What I want to do in this video is just hit some of the highlights of abstract algebra, and particularly I want to talk about the things that will be relevant for us in cryptography. So to start with, a group is a set G with an operation star satisfying the following properties. If A and B are elements in the group, then A star B is also in the group. If A, B, and C are elements in the group, then A star, the quantity B star C, and A star B star C mean the same thing. Okay, so that's associativity. There must exist an identity element, so there must exist some element in the group that we're going to call E, so that when you take A star E or E star A, that's just A. In other words, E is the element in the group that leaves A unchanged. So something like addition with 0. So if you add 0 to any real number, that fixes it. Or if you multiply by 1, those are both, you can think of those as identity elements in a certain sense. So I'll say a little bit more precisely what I mean there. The final thing that we need for a group is that a group, again, is a set G with a property that every element in the group has an inverse. Okay, so for every element A in a group G, there exists what we're going to call A inverse. But in other words, there exists some element B, so that A star B is the identity element. This is the identity from step 3. If we're thinking of a group operation as being multiplication, or even composition, or kind of if you work in general with general groups of multiplication, composition, a few other operations like that, you can think of the inverse like that. We generally write it with the superscript notation. If we're thinking of our group specifically as having an additive structure, so if I'm thinking of, say, the real numbers plus with addition is our operation, then our inverse is just minus A. So it's kind of customary if you have the binary operation of your underlying group being addition, then your inverse is just minus A. So a few examples of groups before we move on. So the first two examples that just come to mind right away are the set of real numbers with addition, and you can just run through the properties. They're closed. If you add two real numbers, you get a real number. If you add three real numbers, it doesn't matter where you put the parentheses. The existence of an identity element. So here, if we're thinking of the reals with respect to addition, the identity element is the real number 0, because A plus 0 and 0 plus A are A for every element in the group, and the existence of inverses. The point here is that for every element in the group, there exists another element in the group, so that when you add them together, you get 0. So for example, the inverse of 5, so specifically thinking about this group in group 1, so that's the real numbers with addition, the inverse of 5 would be minus 5, and the inverse of 12 would be minus 12. The inverse of 0 happens to be 0. But for every real number, there exists another real number, so that you can add those two to get 0. Okay, so the set of real numbers with addition is a group. The set of non-zero real numbers with multiplication is also a group. So if you take any two non-zero real numbers and you multiply them together, you get a non-zero real number. If you were to multiply three non-zero reals together, it doesn't matter whether you put the parentheses around the first two or the last two, you know that product, that A times B times C, means the same thing. Again, whether you have the parentheses like here or like here, doesn't really matter. The identity element in the, so this has a name. So this is the set of non-zero real numbers with respect to multiplication. It's called the multiplicative subgroup of the real numbers. I'm not going to get into the terminology here, but that's what it's called. So that's helpful to know. If you think about the multiplicative group of real numbers with respect to multiplication, then the identity element is just 1, because if you take any non-zero real number and multiply by 1, you get the number that you started with. And finally, the reason why we need to exclude 0 is so that everything has an inverse. So that's the main reason why we needed to exclude 0 there, is so that every element has an inverse. So for example, the inverse of 5 would be 1/5. And in this case, we would use the superscript notation. So if we were to write the inverse of 5, that would be 1/5. Okay, so that's another example of a group. A little bit more interesting example, but for the first two examples, I should mention that there's nothing really special about the real numbers. I mean, the real numbers are a little bit special, but you can think of other general sets like, for example, for number 1, you could have basically any, you could have like the integers, the rational numbers, things like that, that would form a group. For the second set, you have to be a little bit more careful because things need multiplicative inverses. But you could have something like, say, the non-zero complex numbers, or even the positive real numbers would form a group. And so there's a little bit of flexibility here. You could think of some other examples, just kind of looking at those two. For number 3, a little bit more interesting example would be what we're going to call the integers. So this is the integers mod n. I think that this is worth writing. So this is the set of integers mod n. That's what I mean when I write the z sub n. And so, for example, z sub 10 is just the integers 0 through 9. And I could have also picked, say, the integers 10 through 19, because remember, what we're really doing is working with equivalence classes under the equivalence relation, where two integers are congruent if they're two integers are equivalent if they're congruent mod 10. But it's just customary to work with the integers 0 through 9 in this case. I think that's the best way and the least confusing way. The set operation that we're going to work with here is addition mod n. And so what that means is that you're going to add two numbers, and then you're going to look at what is that number mod n. And so if you were to take 4 plus 7, you will get 11. Mod 10 is 1. And so if you add 4 and 7 in this group, you end back up in the group. Here you get 1, for example. Here we're thinking of, this is a kind of addition. So we would specifically write the inverse as minus. So the inverse of 4 would be minus 4 or 6, if you want to think about it that way. So that is the set of integers mod n. We will come back to this idea multiple times. This turns out to be a very important idea in lots of different areas of math, and this is going to be the set that's going to be very useful for us when we're working in cryptography, and we'll talk a little bit more about that at the time. Another example of a group is the set of permutations on a set of n letters. So just to make this more concrete, here our operation would be composition. But just to make this more concrete, let's say that we have capital X is our set, and we're going to work with S sub 3. This is called the symmetric group. Okay, so this is the symmetric group. These things all have names, so that helps us kind of look back and learn different facts about these sets or about these objects. But the symmetric group on the set with 3 letters, I don't know why they say n letters or 3 letters. It's their numbers 1 through n, but all they mean by letters is objects, really, because it doesn't matter what these actual elements are. So here we just have our set X is the set 1, 2, 3. And when I say permutation, what I mean by a permutation is a way, so permutations and combinations are something that we talked about in the combinatoric section. And really, a permutation is just an arrangement. I think that's a good way to think about the word permutation in general. In this context, a permutation really means a bijective function. So in other words, what you're going to do is you're going to think about, if you have your domain is 1, 2, 3, and your codomain is the set 1, 2, 3 again. So this is bijective functions on the set, meaning bijections from this set to itself. In our case, from the set 1, 2, 3 to itself. Here we're going to have 6 possible bijections. And that's because 3 permute 3 is 6, right? Because you have 3 times 2 times 1. You have 3 times 2 times 1 because there's 3 terms. So there's 3 factorial, there's 6 permutations. In general, in S sub n, you'll have n factorial permutations to talk about. But for S3, you have 6, so we can just write them down. And these are the 6 different bijective functions that we have on the set 1, 2, 3. So we have the set that just leaves everything fixed. And then we have, so I'll call that sigma 1. and then we have sigma 2, 3, 4, 5, and 6. Okay, and so you can see that these are all the different bijections. You can just go through and try and think about where does each element go, and you'll see that it's got to be one of these 6 sets. Now, I want to point out that it's not possible if you were to have, say, 1, 2, 3, 1, 2, 3 as your domain and codomain. It's not possible for it's not possible for 2 elements in the domain to go to the same element in the codomain, because we're specifically talking about bijections, and in particular they have to be onto. So we need to be really careful. And actually, that function that I drew was neither onto nor one-to-one, so it didn't have either property. Again, we know that a bijection on a finite set, one of the things that we talked about, I'm not sure if we proved this or not, but if you have a finite set and you have a bijection from that set somewhere else, then so if you were to say have the set, let's call this E, this set 1 through n. So if you were to have a bijection from E to E, it turns out that that function will be a bijection, or it'll be 1-to-1 if and only if it's onto. So 1-to-1 and onto kind of come together when you have these finite sets. Anyways, S3 is the set of functions on the set 1, 2, 3, and you can think of these 6 bijective functions here. Now, our operation that we're going to use to combine these functions is composition. So, for example, if you were to take sigma 6 composed with sigma 2, okay, what this would mean is just the normal composition. You would have sigma 6 of sigma 2 of 1. Now, sigma 2 is going to be this function here. And so we need to think about, where does 1 go? Well, 1 gets mapped to 1. So that's why sigma 2 of 1 is just 1. And then we're going to look at what happens to sigma 2 of 2. Well, that gets mapped to 3. So sigma 2 of 2 is 3. And finally, 3 gets mapped to 2 in this function sigma 2. So sigma 2 of 3 is 2. And now you can go back and think about, forget about sigma 2, just think about, what do these inputs do for this function sigma 6? Well, sigma 6 of 1 is 3. So if you take 1, that gets mapped to 3. 3 gets mapped to 1, and 2 gets mapped to 2. So this leaves you with these outputs. And it turns out that if you think about now a function that maps 1 to 3, 2 to 1, and 3 to 2, that's nothing more than sigma 5. That maps 1 to 3, 2 to 1, and 3 to 2. So it turns out that sigma, I don't want to ruin anything here, but sigma 6 composed with sigma 2 is just sigma 5. And in this sense, when you compose 2 elements, here we took our binary operation, and so this shows that the set is closed, because if you were to combine these 2 operations, you get another function, in this case sigma 5. We know lots of stuff about bijections, right? You know that a composition of bijections is a bijection, so that tells you automatically that that's also going to be another set in S3, because this is the set of all bijections from the set 1, 2, 3 to itself. We can also talk about inverses, because again, when you have a bijection, you have inverses. So if you were to have sigma 5 inverse, what this would mean is, what function do you have to compose with sigma 5 to get the identity? And I should mention, what is the identity? Well, the identity is the function, so that when you compose that with something else, it leaves the first thing fixed. So in this case, the identity function turns out to be this function sigma 1. This is the identity. And the reason why that's the identity is that this is the function, so that when you compose it with the other functions, you get whatever the other function is. So for example, sigma 1 composed with sigma 4 is just sigma 4. You can check that that's true. So that works for, that works for every function, not just sigma 4. Okay, so sigma 1 is the thing that you have to combine with the other functions. You have to compose it with the other functions to get the other quantity. Likewise, we have inverses. So the function that you have to compose with sigma 5 to get the identity element, which is sigma 1, the thing that you have to compose with sigma 5 is sigma 4. So we would write that the inverse of sigma 5 is sigma 4, and so on. Okay, so this is an interesting group. I'm just going to leave it here. There's a lot more to say about this object in an abstract algebra class, but for now we just want to introduce the idea of a group. So this is a good, interesting example. One more good, interesting example is what's called the multiplicative group mod N. Okay, so this is again the multiplicative group mod N. And here, multiplicative group, what this means in this case is I want to just emphasize that this is an X here. So pay attention to the fact that this is an X, or like a times symbol. And before, what we had was a star, which means non-zero. Okay, so those are, it's important, they're closely related, they look like each other, but they're two different elements. Here, this X specifically refers to the elements in the set of integers mod N that have multiplicative inverses. And we saw that if you were to think about, so one of the things that we saw when we were talking about solving linear congruences is that if you were to try and solve AX is congruent to 1 mod M or mod N, it doesn't really matter, we know that there's going to be an inverse. So A inverse exists if and only if, so if and only if A and M are relatively prime. So that's why the elements in the set of integers mod N that have inverses are precisely the ones that are relatively prime with N. Okay, so this is just a fact from what we did not too long ago, but 1 or 2 weeks ago. So this is called the multiplicative group of integers mod N. Again, I'm trying to avoid too much jargon, but for example, z sub 12 is going to be just the set of integers 1, 5, 7, and 11, because z12 consists of 0 through 11, and 0 is out. 1 is relatively prime with anything, so this set will always have a 1 in it. 2 is not relatively prime with 12. 3 is not relatively prime with 12. 4 is not relatively prime. 5 is relatively prime, so 5 and 12 have no prime factors in common. 6 is not relatively prime, nor is 8, because they are both, so 8 and 12 are both divisible by 4. In particular, they're not relatively prime. The other relatively prime integers from 0 to 11, the ones that are relatively prime with 12, are just 1, 5, 7, and 11. So it turns out that there's 4 of them. The number of integers that are relatively prime with N that are also less than or equal to N is denoted by this function phi of N, which is a function that we saw before when we talked about Euler's theorem and Fermat's little theorem. So this phi of N is called Euler's Totient function. And so this is a function that we've seen before a little bit, and we'll work a little bit with this as we go on. So this function, Euler's theorem, will play a role for us specifically when we talk about cryptography. Okay, if you look at the group Z11 and you look at the multiplicative group, this is going to be everything but 0. So it turns out that here the X, the time symbol, and the star would be the same thing. If you just remove 0, you get the multiplicative group, or what's called the multiplicative subgroup. Again, I want to avoid too much jargon here. But the reason why everything from 1 through 10 is relatively prime with 11 is because 11 is prime. So this is actually a property of primes, that if you take any prime, p, and you look at the multiplicative group zp, this is just going to be that set zp without, without 0. Okay, so everything from 1 to p minus 1 will be relatively prime with p if p is a prime. Okay, because p is not divisible by any number less than p besides 1. So these are just some examples of groups. Again, I think that the most important example that we've talked about so far, at least the one that will be most relevant for cryptography, is this example number 5.